In this online lecture, we're going to discuss the Wittig reaction. Very important here. Let's talk about our key points. This is what we're going to learn. Number one, the Wittig reaction converts a carbonyl into an alkene. That's going to help us with quick product. Number two, preparation of ylides is at the mercy of SN2 restrictions. This is going to help us in synthesis. And number three here, stabilized ylides form E-type double bonds, and unstabilized ylides form Z-type double bonds. Remember, key point 1 says we're converting the carbonyl into an alkene. And if you remember from a previous online lecture, some alkenes come in E versions and Z versions. So let's dig into our reaction here. Let's start with the overall big picture here. Notice we're starting with, let's say, a ketone here, and let's color the carbonyl carbon here yellow. And this reagent right over here, let's color this carbon orange. We're going to be calling that carbon the phosphoylide carbon. The phosphoylide carbon, notice, is always directly connected to that phosphorus. But let's look at what happens here overall. What we're doing is that this carbon right here, the yellow carbon, came from the carbonyl carbon. We're simply connecting that carbonyl carbon to this carbon here, which is the phosphoylide orange carbon. Our overall product here, notice, is an alkene. And what I just showed you here is the quick product method. We simply know to link the yellow carbonyl carbon to the orange phosphoylide carbon, and remember that there's a double bond between them. So let's look at some examples using the quick product method first here. Notice if you wanted to get the product of this reaction, you would notice you have a carbonyl, and this would be your yellow carbon, and right here this would be the phosphoylide carbon. You would also notice that this is definitely the Wittig reaction because only the Wittig reaction has this PH3P and then R group. So it'll be very obvious on your Orgo exam that you're dealing with a Wittig reaction because this reagent is unique to this reaction. So back to our quick product method here, all we're going to do is connect the carbonyl carbon to the phosphoylide carbon. So again, this carbon came from the carbonyl, this carbon came from the phosphoylide, which is, again, this carbon right here. And notice that carbon has an H directly connected to it and a methyl, and that's exactly what we see in our product. Let's look at one more example to make sure you got this quick product method. Again, what is the product of this reaction? You're going to focus on the carbonyl carbon here in yellow, the phosphoylide carbon here in orange, and that means connecting them and putting a double bond between them gives us this product right here, with this carbon coming from the carbonyl and this carbon coming from the phosphoylide. And again, notice the phosphoylide carbon has two hydrogens directly connected, and that's exactly what we see in the product. And of course, notice the double bond between those two carbons in the product. Now, let's dig deeper into this reaction in terms of how do we make a phosphoylide and what is the mechanism? But let's get an understanding of our phosphoylide first. Here's what it looks like in general. Again, it always has the PH3P connected to a carbon, and that carbon is going to have two groups connected to it. Sometimes two alkyl groups, sometimes an alkyl group and an H, and in the last example we saw, sometimes just two hydrogens. And let's pay attention to some of the resonance that this structure has. Notice you're technically allowed to make this resonance move. You can say the pi electrons in the double bond there jump up onto that carbon. If that happens, you end up with this as a resonance structure. It's this structure located in the bottom right that reminds us of how these molecules react. Notice with those two electrons and that negative charge on the carbon, that simply makes this carbon very nucleophilic. So let me show you how to apply this to a reaction. Let's say you want to generate the product of this reaction, but you choose to think through the mechanism. You would begin by taking your phosphoylid here and representing not the structure you see in front of you, but its residence structure, which would look like this. Again, notice that means the carbon there is very nucleophilic. So the first step of this reaction is simply that nucleophilic carbon attacks the carbonyl and boots the electrons up on the O. This is our, remember, attack step. Remember, we learned before in previous online lectures that aldehydes and ketones typically participate in attack and protonate reactions. So far, this Wittig reaction is following the general mechanism. And let's see what we would get here after the attack step. This is what you would get. Let's make sure you can see the connections we made here. This yellow carbon here and the phosphoylid carbon here would be this yellow carbon right here, and this would be the phosphoylid carbon here. Take a few minutes and make sure you see how we ended up with this. So that's our attack step, and let's keep going. Now remember, we've seen before attack and protonate, but to help you remember the mechanism here, think of this as attack and then phosphorylate. Notice I'm having the electrons move on the oxygen to that phosphorus, so it's almost like we're phosphorylating the oxygen instead of protonating it. The result of this move is this product right here. And don't just memorize this, think about why that oxygen would want to attach to that phosphorus, because notice the oxygen is negatively charged, the phosphorus is positively charged, therefore there's an electrostatic attraction there. However, the result that we get, notice, is a four-membered ring, which means this thing is not very stable. And because of that, that means that this thing further reacts. Which brings us to the last step of the mechanism here. To relieve this four-membered, highly strained ring, the electrons within this four-membered ring circulate, which means these electrons move this way, and these electrons move down that way. Let's see why there's an incentive for this to happen. Notice, following this arrow movement, that means that if the electrons moved from here to go between the phosphorus and the oxygen, that means this bond the arrow is pointing to is going to break. And that also means that right here, if the electrons move this way, a double bond is going to form between the oxygen and the phosphorus. And for the other electron movement, notice that arrow means that this bond is going to break, and that means that we're going to form a double bond between these two carbons. That gives us a product that looks like this, and it gives us a side product that looks like this. Take a few minutes and make sure you see how that arrow movement leads to these products on the right. And notice, look at what we have here. We have an alkene. And again, our alkene came from 1, a carbon originally in a carbonyl group, and 2, a carbon originally in a phosphoylid. So this is the mechanism of the Wittig reaction. We should also know, however, how to make a phosphoylid. For instance, let's say we want to make this particular phosphoylid right here. What you first do is start with triphenylphosphine, and we simply add an alkyl halide to him. But not just any alkyl halide. For instance, again, if we want to make this particular phosphoylid, our phosphoylid has a 2-carbon long alkyl group here in blue. This part of the phosphoylid comes from the alkyl halide. So the R group of the phosphoylid determines the size of our alkyl halide that we're going to use. And this first reaction is actually a reaction we've learned before. What happens here is simply the electrons on the phosphorus attack this carbon right here and boot off the Br. This happens in one swift step, so that makes this reaction an SN2 reaction. The product would look something like this. Notice the phosphorus takes on a positive formal charge. But this is not our phosphoylid. We need to do one more reaction to officially make the phosphoylid, and that is adding N-butyllithium. All we need to know about this molecule is that it's a very strong base. And what this strong base does is rip off the hydrogen connected to the phosphoylid carbon. If this happens, we're going to get this as a conjugate base. And notice right here is your phosphoylide. If you can't see that right away, notice if you took the electrons on the carbon and dropped them down to here, which is basically performing a resonance move, then you would get this structure right here. Notice these are the two resonance structures of a typical phosphoylide. So our preparation of phosphoylids simply involves an SN2 reaction of an appropriate alkyl halide followed by a strong base. Now, just in case, please make sure you know about the PH3P molecule, that its actual structure is this right here. Remember, pH is short for phenyl, so this molecule has 3 phenyl rings directly connected to a phosphorus. Your organic chemistry exam may have either version of this molecule. So now that we know the mechanism of this reaction, and now that we know how to prepare a phosphoylide, let's look at some of the nuances of this reaction. For instance, there's a difference between what's called a stabilized and an unstabilized ylide. What you see on the top here is a stabilized ylide, and the reason why he's stabilized is because you can draw a resonance structure that delocalizes the double bond in the phosphoylide. In fact, here's what the resonance move would look like. The double bond electrons would move this way, and the electrons within the carbonyl would boot up on top of the oxygen. Remember, delocalization is stabilizing. So therefore, we would call this a stabilized ylide. But notice the ylide below. It wouldn't have resonance. There's no place to move the pi electrons in the double bond in this phosphoylide. So he would simply be called an unstabilized ylide. Now, what does this mean for us in terms of reactivity? Well, look at this example right here. Let's say on an organic chemistry test we want to get the quick product of this reaction. But before we connect our carbons, let's notice that we have a stabilized ylide here. Notice how this affects the product that we get. So, applying our quick product method again, remember, the carbonyl carbon here in yellow would be directly connected to this orange phosphoylide carbon, which would give us something that looks like this. Again, this carbon right here is directly connected to the phosphoylide carbon here. But let's rearrange this alkene product that we got here to look like this. This is the actual product that we would get. This double bond happens to be an E-type double bond. Remember, we've learned this before in a previous online lecture, and to make sure you see this, let's verify that this double bond is actually E. Remember, the method we talked about is you have your dashed line that runs parallel to the double bond, and you look at the priorities across this dashed line. On the left side, the methyl would be high priority compared to the H being lower priority. And on the right side, the carbonyl group would make this group higher priority and make the H lower priority. And remember, when our low priorities are trans and our high priorities are trans, overall we say this is an E-type double bond. And what we're learning here is that stabilized ylides form E-type double bonds. What we're kind of looking at here is the stereochemistry of this reaction. Let's say you're taking a multiple choice organic chemistry test. Your test may have 2 possible answer choices if it's multiple choice, where one of the answer choices is this molecule in the E format, and the other answer choice is in the Z format. You would have to know to pick the E double bond as the correct answer. So we must remember that stabilized ylides form E-type double bonds. Let's look at another example here to make sure you got this. Notice in this example, we're reacting an unstabilized ylide. Let's see how this affects the product. Again, using the quick product method, we would connect this carbon in the carbonyl to the phosphoylide carbon here, which would give us this as a product with the appropriate connections. However, rearranging this alkene to the correct answer, it would look like this right here. Notice this particular alkene is in the Z format. And again, just in case, let's investigate that. Here is our dashed line, and if we look at the priorities, you're going to see that this is how they're set. The hydrogens are lower priority, the non-hydrogen groups are higher priority. And remember, if your lows and highs are on the same side or cis, then the double bond is a Z-type double bond. Our take-home message here is that unstabilized ylids lead to Z-type double bonds. So this is why we first want to register if our ylid is stabilized or unstabilized. However, let's look at a very popular test question concerning the Wittig reaction. Here it is, sample problem 1. Provide the necessary carbonyl compound in phosphonium or phosphoylid to yield the following alkene. So notice we're going backwards. They're giving us the alkene product, and we want to figure out the correct carbonyl and phosphoylid to make this molecule. Well, remember, if we know our quick product method very well, then it shouldn't be too hard to go backwards. Think about it. You would look at the alkene and you would say one of the carbons within the alkene has to come from the carbonyl, let's say, and the other one in the alkene would have to come from the phosphoylid. The question is, which one should come from which? Should it be this right here, or should it be this right here? Well, remember, let's go back to our phosphoylid preparation. Remember, the preparation of phosphoylids involves an SN2 reaction. Remember, the triphenylphosphine has to attack this carbon and boot off the bromine to get this thing right here, which means that this carbon right here, the phosphoylid carbon, was the original carbon in the alkyl halide. And if you remember, a fact about SN2 mechanisms is that this carbon needs to be accessible, or in other words, as less substituted as possible. Remember, if this orange carbon were, let's say, tertiary, then it would never participate in an SN2 reaction. Only methyl carbons, primary carbons, and secondary carbons can be attacked in an SN2 mechanism. So, to increase our yield in a Wittig reaction, we want the phosphoylid carbon to be as less substituted as possible. That means, going back to our example problem here, you would look at each carbon within the alkene and ask yourself which one is more accessible or less substituted. Notice the carbon right here at the arrow has technically 3 carbons directly connected to it, and this carbon has directly connected to it only 2 carbons. Since he's less substituted, we'd like the phosphoylid to come from this carbon, which means the other carbon would have to come from the carbonyl, the yellow carbon. Now that we've figured this out, it's easy to take these back to the reagents. For instance, let's start with the yellow carbon. Remember, if we decided that he has to come from the carbonyl, we simply turn him back into a carbonyl carbon like this. And notice he retains his 2 methyl groups that were directly connected to him. Now, to take care of the other side, the phosphoylid side, we simply take our orange carbon and double bond him to a phosphorus pH3 group, like this. Notice he has his 2 carbons connected to him in the product, so they would also have to be connected to him originally in the phosphoylid. So this would be the answer. This particular combination would give us the best possible yield. So that means if your organic chemistry test was multiple choice and you could only pick one answer, this would be the one that you would want to go with. However, you don't have to perform this reaction this way. In fact, you can actually make this carbon the phosphoylid carbon and this carbon the carbonyl carbon. If you did it this way, then taking this back to its reagents, let's again start with the carbonyl side, the yellow carbon. This would be the original carbonyl group. And that would make the other carbon, the orange carbon, this the phosphoylid carbon. Notice if you put these 2 reagents together using the quick product method, you would get the alkene that you see on the left. But let's make sure we can see why this would work. Again, notice this is the phosphoylid carbon. If we wanted to prepare this phosphoylid, it would look something like this. Again, The electrons on the phosphorus would attack this carbon and boot off the Br. And this orange carbon happens to be a secondary carbon. And remember, secondary carbons are acceptable for SN2 mechanisms. So that means that this is another possible answer. It's a good idea to know if there is more than one way to make a particular alkene via the Wittig reaction. Because on some organic chemistry multiple choice tests, a professor might ask you, give more than one way to prepare this alkene. So there could be more than one answer, which means it's possible to write a test question where the answer in this case would be D, all of the above. However, remember, if all of the above is not an option and you could only pick one answer, then you wouldn't want to use this combination in front of you. You would want to use the previous method because, again, that had the phosphoylide carbon being less substituted. So let's look at another example to make sure you got this. Again, working backwards, we want to provide the necessary carbonyl compound and the phosphoylide to make this molecule. Like we said before, you would focus on the carbons within the double bond. You'd be looking at this carbon right here and this carbon right here. And you'd ask yourself, which one should come from the carbonyl? Which one should come from the phosphoylide? The phosphoylide carbon, again, should come from the less substituted. And notice that would be this carbon right here. He is less substituted than the carbon on the left. So that means the carbon on the left should come from the carbonyl. So that means, working backwards, we would turn the yellow carbon here back into a carbonyl carbon, and we would turn the orange carbon into a phosphoylide. So this is the answer for the best possible yield. However, just in case, you can actually do it the other way around, and doing it the other way around would yield this as an answer. Notice in this case, the carbonyl carbon became the right carbon in the alkene, the yellow carbon, and the left orange carbon came from the phosphoylide. Although that phosphoylide carbon has that very bulky benzene ring, it still can potentially be attacked in an SN2 mechanism. So what have we learned here? What are our key points? Well, number one, the Wittig reaction again converts a carbonyl into an alkene. And two, remember, preparation of ylides is at the mercy of SN2 restrictions. And third key point here, stabilized ylides, remember, form E-type double bonds, and unstabilized ylides form Z-type double bonds.